Okay, so we are going to now, we're done with the first order stuff. We're going to go back to the same equations that we were looking at in the beginning of the, I was going to say the beginning of the year, but the beginning of the summer, only now we're going to be looking at a finite domain. So for example, we're going to start with the diffusion or the heat equation, and we're going to say that the t derivative of u is equal to the double x derivative of u. We're going to say that we know that u of x0 is equal to some given f of x. But one thing that I haven't made explicit yet is that we're only looking at the interval from 0 to 1. So we're only looking at the interval from 0 to 1. And to this, we're going to add boundary conditions. In other words, we're going to assume that we know that u of 0t is equal to u of 1t, and these are both equal to 0. Okay, so what this is modeling, for example, if u is the temperature of a rod, what this is modeling is the temperature of a rod whose initial temperature profile is f of x, and at the left-hand endpoint and the right-hand endpoint, the temperatures there are kept to 0. They're held at 0. Sorry, I keep forgetting to silence my phone. Okay, so how does this change things? Well, in a certain sense, well, it's going to change things a lot in the mechanics of the problem. We could view what we have done before, all the Fourier series stuff, as a boundary value problem, just where we have u of minus infinity and u of positive infinity. Both of those are equal to 0 in the limit sense. But this is what we're going to model here. So what we're going to do, and I might, I'm going to sort of show you what we're going to do for a few problems, and then after that, I'm going to kind of go back and look at the big picture of this, kind of see exactly what's going on, and relate it back to what we had been doing at the beginning of the class as well. So what we're going to do, what our strategy is here, sorry, my black marker went out. What our strategy is, which might not make any sense right now, there's no particular reason to think that this is a strategy that's going to work, but it's something that we can try because it lets us get some formulas. So what we're going to want to do is we want to look for solutions of the form u of xt is equal to some function phi of x times some function h of t. Now, the choice of letters phi and h is somewhat arbitrary, but idiomatically, as we will see, there's a reason that I'm picking phi of x and h of t rather than phi of t and h of x or some other letter. So there's sort of an idiomatic principle that's going on here that's just sort of standard conventions. But once we do more and more problems, you'll see why I picked phi to be the one it is. But just go with it for now. I know it looks a little, we have a Greek letter there and a Latin letter there, and so it's not completely, it's not clear why we're doing it that way. There is a way, just go with me for a minute. Okay, so what's going to happen if we take this and plug it into the equation? If I take the derivative of this with respect to t, it's just going to be phi of x times h prime of t. And on the right-hand side, if I do the double derivative and the x derivative, it's going to be phi double prime of x times h of t. And this might be familiar from a previous homework problem. If we rearrange this, we're going to get h prime of t over, h prime of t over h of t is equal to the double derivative of the function like this. Now this is a function of t, and this is a function of x. And this is true for all values of t and x. So whenever we have something that's just a function of t and just a function of x, and they're equal to each other, it means they have to be equal to a constant. So we're going to say that this is equal to minus lambda. So lambda here is a constant. It's obvious, a good question is, why am I using minus lambda instead of lambda? In other words, why didn't I just pick the constant to be lambda instead of minus lambda? That will make sense in just a moment. Okay, so now what we have are two ordinary differential equations. If I look at the t equation, I've got h prime of t is equal to minus lambda h of t. Or the way that I really want to think about it actually is h prime over h is equal to minus lambda. However you want to think about it, this is going to give h sub lambda. So for every if I look at that equation, for every lambda, I'm going to get a different solution. So h sub lambda of t is going to be equal to some constant that for now I'm going to call c sub lambda, and it's going to be e to the minus lambda t. The notation is going to change slightly, and there's going to be several other constants that are going to get rolled into one constant. And actually, we'll toward the end of this, we'll see that we're not going to index h with lambda. It'll be indexing with the square root of lambda, which might not make sense now, but it will make sense later. Okay, so this is what h of t is. This is all we can say about h. But for phi, we can say a little bit more. So if you look at phi, you've got phi double prime of x is equal to minus lambda phi of x. Now, I will prove in a moment that lambda is greater than 0. Probably in another video. I'm going to show that lambda is greater than 0. So I'm going to show you that later that lambda is greater than 0, strictly greater than 0. So let me back up a second. We don't know if, with just this equation, we don't know that lambda is greater than 0. However, if we add the boundary conditions, phi of 0 equals phi of 1 equals 0, then we do know this. Where do these boundary conditions come from? Well, we know that u of 0t and u of 1t are going to be equal to 0 for all values of t. So in other words, if I look down here and I plug in x is equal to 0, this function is going to be equal to 0 for all values of t. The only way that can happen is if phi of 0 is equal to 0. I mean, if h of t is identically equal to 0, we don't care about the solution that's identically equal to 0. So if h of t is not equal to 0 for all values of t, this means that phi of 0 has to be equal to 0. And similarly, u of 1t is equal to 0. So if I plug in a 1 there, this means phi of 1 has to be equal to 0. Okay. So this is a new type of differential equation probably than what you've seen before. So typically when you have a second order equation, you need two conditions. But it's not conditions on the function. It would be like phi of 0 is equal to something and phi prime of 0 is equal to something. But what we have now is phi of 0 is equal to phi of 1, and they're both equal to 0. It's called a boundary value problem. So we know what the unknown function is. We know the values of the function at the endpoints of the interval in question. In this case, going from 0 to 1. Well, in a case like this, as I will show you in an upcoming video, there's only, and as we'll see more in this video, there's only certain values of lambda that will give you a solution to this differential equation. In other words, there's not solutions for every value of lambda that you can put there. The first thing that we can say, and this is what I'll show you in an upcoming video, is that lambda is strictly greater than 0. Okay, so for this equation to have any solutions at all, lambda has to be strictly greater than 0. Okay, so we don't know what lambda is. At this point, we just know they're equal to some constant, and we're calling it minus lambda for now. But we don't know, at this point, we don't know what lambda is. At this point, we know a little bit more about lambda if you know are okay with this fact that lambda is greater than 0. So now if lambda is greater than 0, minus lambda is less than 0. If minus lambda is less than 0, the general solution to this is going to be phi sub lambda of x is going to be equal to a cosine square root of lambda x plus b sine square root of lambda x. And now what we're going to do is we're going to use our initial our boundary conditions, our boundary values, to figure out what a and b are. So if you plug in phi of 0, or if you plug in x is equal to 0, you're going to get 0. And what's going to happen over here? Well, if you plug in x equals 0, this is cosine of 0, which is just 1, so this is a. All right, so this tells us a is equal to 0. So let's just get rid of this term. So a is equal to 0. All right. If you plug in 1, if you plug in x is equal to 1, you also get 0. So 0 is equal to phi lambda of 1. And we're going to plug in 1 over here to get b sine square root of lambda. Now, we have a product of two things. If it's equal to 0, one of the factors is 0. So if b is 0, then it just means phi lambda is the 0 function, and we don't care about that, because if phi lambda is the 0 function, our solution is just the 0 function, and that's not really exciting. It's not going to satisfy this initial condition. Okay, so we don't want just the 0, the u of xt equals 0 for all x and t solution, because that's not, it's not a very interesting solution, and we can't do anything with it. Now, if f of x is equal to 0, then that's going to be the solution. But aside from that, it's not going to be something that we care about. Okay, so then what we can conclude then is that sine of the square root of lambda must be equal to 0. So we can conclude that the sine of the square root of lambda has to be equal to 0. Well, let's think about it. If sine square root of lambda is equal to 0, what does it mean? It means the square root of lambda has to be equal to k times pi, where k is an integer and k is greater than or equal to 1. Okay, so what does this mean? Phi lambda of x is equal to b times sine of k pi x. So what this tells us is for every k, we're going to get a different lambda here. It's going to be equal to minus k pi squared. So for only the values of lambda that satisfy that are going to give us a solution. Sorry about that. Only the values of lambda, where the square root of lambda is equal to k pi, lambda greater than 0, these are the only values of lambda that are going to give us a solution here. And for each one of those different values, for each one of those different k's, we get a different solution. Sine k pi x is going to be the phi solution, and then h of t, this lambda is k squared pi squared. Okay, so now what we're going to do, let's back up a second. Given this, we're going to write the solution in the following way. We're going to call it u sub k. U sub k of xt is going to be equal to our h function, which is e to the minus k pi squared t, times the phi function, which is sine of k pi x, and we're going to say multiply it by a constant bk. Okay, so why am I using bk instead of ak? Well, we're going to look at some solutions like this for some problems. These are going to be sine functions, in which case we're going to use bk. Sometimes they will be cosine functions, in which case we'll use ak. You don't have to, it's just a convention, but it's a convention I'm going to follow. So what we have just shown is that for every k, this function here is a solution to the differential equation, so check, and the boundary values. We do not know, and in general, unless f of x happens to be equal to some constant of a sine function like this, this is not necessarily going to be a solution or going to satisfy the boundary condition here. Okay, so all we've done so far is we have found a function that satisfies the PDE and the boundary conditions, unless f of x just happens to be a multiple of a sine function. This is not going to be a solution, or is not going to satisfy the initial condition. So maybe it looks like we haven't made any great strides to solving this, because it sort of seems like, well, in the odd case that f of x is a sine function, then we're good, but most functions are not sine functions, so yeah, what's going on here? So let's think about it this way. Let me come over here. let me record this information over here. So we're saying that UK of xt is equal to the sum, sorry, not equal to the sum yet, it's equal to this, some constant bk times e to the minus k pi squared t sine of k pi x. Okay, so UK of xt is equal to this expression here, but notice that if I plug in t is equal to 0, UK of x is 0 is equal to bk sine of k pi x. Okay, now unless f of x is equal to sine of k pi x for some k, or a multiple of sine of k pi x for some k, this is not going to satisfy the initial condition. But maybe we can look at something a little more general than just f being equal to one sine function. What if we know f of x is equal, let's say we know f of x is equal to 2 sine 3 pi x minus 2, let's say the different one, minus, or let's say plus 4 sine 19 pi x. Okay, think about if you can figure out, using what we've done here, if you can figure out what a solution to this problem is if f of x is equal to that. Okay, so what about this? U of xt is equal to 2 e to the minus 3 pi squared t sine 3 pi x plus 4 e to the minus 19 pi squared t times sine of 19 pi x. Is this a solution to this problem here if that's what f of x is equal to? So when I say a solution to this problem, I mean the PDE, the boundary conditions, and the initial condition. Is this a solution? The answer is yes. So why is it a solution? Well, first of all, if you plug in t is equal to 0, that goes away and that goes away. And you have 2 sine 3 pi x plus 4 sine 19 pi x, so it satisfies the initial condition. If you plug in x is equal to 0, you have sine of 0 and sine of 0, so this is going to be equal to 0. If you plug x is equal to 1, you have sine of 3 pi, that's equal to 1. Sine of 19 pi, sine of 3 pi is equal to 0. Sine of 19 pi is equal to 0. So it satisfies the boundary conditions. So we just sort of, by what I just said, it satisfies the initial condition and the boundary conditions. Why does this satisfy the PDE? Well, let's think about it like this. So I can write this as u of xt is equal to 2 times u3 of xt plus 4 times u19 of xt. And notice there's already a bit of ambiguity here. Is the bk included in the definition of uk or not? In this case, I'm not. I'm thinking about this just being equal to uk, and so we have something like this. There's a lot of sort of there's a lot of different ways to express these ideas, and sometimes we want to include bk there, and sometimes we don't. This is one of the times when we don't. Okay, so if I take the derivative with respect to t, so I want to show that this satisfies the PDE. If I take the derivative of this with respect to t, so the t derivative, now here's the important thing. This is a linear equation. So since the t derivative is linear, since all derivatives are linear, this is going to be equal to the to 2 times the t derivative of u3 plus 4 times the t derivative of u19. But what do we know about u3 and u19? Well, it just, it's one of these uk's, meaning it's a solution to the PDE. So this is equal to 2 times the double x derivative of u3. I'm going to stop writing the arguments because it's getting to be too tedious. And then the u19, the t derivative of u19 is going to be the double x derivative of u19. With a 4 there. 4 times the t derivative of u is 4 times the double x derivative of u19. Okay, well again, the double x derivative is linear as well. So this, I will write this and stand out of the way in just a second, is equal to the double x derivative of 2u3 plus 4 times u19. So overall, and then this right here in the brackets is just equal to u. So the t derivative of u is equal to the double x derivative of u. And so that proves what we wanted to prove. It proves that it also satisfies the PDE. Okay, well, in general then, if you know that f of x is equal to the sum k equals 1 to n bk sine of k pi x. If you know that f of x is equal to that, then you know that u of xt, the solution to this problem right here, is going to be the sum k equals 1 to n bk e to the minus k pi squared t sine of k pi x. In the example we just looked at, we could say the sum goes from k equals 1 to 19, and all of the bk's are equal to 0 except b3 was equal to 2 and b19 was equal to 4. So if we know f of x has this form here, then we know u of xt is equal to that. And that will solve this problem that I have here. That will solve the heat equation with these initial conditions and boundary conditions. Okay, so there's a lot of questions to be answered here. One, I need to explain why lambda is greater than 0. That's going to come much later. Two, I need to explain, okay, well, what happens if f of x is not written like that? Or should we expect that f of x will be written like that? Or what's going on? So I've made this a little more general than what we saw just, in a solution like this. Now, if we happen to know that f of x is a linear combination of sine functions, then we can solve this function. But x squared isn't a linear combination of sine functions. 1 is not a linear combination of sine functions. Unless we just write down a linear combination of sine functions, the functions that we're thinking about for f of x, it's not going to be a linear combination of sine functions. So then how do we deal with that? So I need to explain that also. Like why does this, in other words, why is what we are doing here getting us any closer to a solution to this problem in the general case when f of x is not equal to a linear combination of sine functions? So I will do all of that in upcoming videos. But the number one thing that I want you to know now, we're looking at a finite domain. So we add these boundary conditions. Physically, the ones we have here say we are holding the temperature of the ends of the rod at 0. We'll look at other boundary conditions later. We looked for solutions of this PDE that also satisfied the boundary conditions that were product solutions. In other words, a function of just x times a function of just t. When we did that, we got two different equations. One was the t equation we called that the h function, and one, the x equation, was the phi function. These are the things that we figured out were solutions. For every k, we get a different solution, and this is based on the fact that the lambda that we had when we did this method has to be positive, and the boundary conditions say that in addition, the square root of lambda has to be of the form k pi for k greater than or equal to 1. This is what we have so far. As we go on, this will start to make a little more sense, but this is the basic outline. And so now what I'm going to do in the next video is explain, can we and how can we and in what sense can we assume that f is a linear combination of sine functions? Because if we can't assume that f is somehow a linear combination of sine functions, then this doesn't really get us any closer to a solution do this problem outside of the limited cases when f literally is just equal to a linear combination of sine phi.